All right, we're going to look at an example in order to develop the formulas for permutations and combinations. What are the formulas? Where do they come from? Why are they what they are? And we're going to look at the example of the 1992 Dream Team, the year that Team USA decided to take the best NBA players and use them in the Olympics. Because prior to that, they had a few disappointing Olympics where they were using amateur players only. Team USA, the Dream Team, went through and just destroyed everybody by 30 to 40 points on average. It was crazy. And it was a phenomenal team of some all-time greats. You got Michael Jordan, Magic Johnson, Charles Barkley, Karl Malone. You can see him on there, Larry Bird. Anyway, what we're going to look at first is pretend you're the coach of the Dream Team, Chuck Daly, and you're trying to find the total number of lineups that are possible. And I did include some numbers in front of these players. That's like their positions. If you use the kind of common numbering system for basketball positions, where 1 is a point guard, 2 is a shooting guard, 3 is a small forward, 4 is a power forward, and 5 is a center. However, we're going to kind of ignore those for the purposes of thinking of all of the possible lineups, because there's no rule that says that Magic Johnson has to play point guard. You could have him play shooting guard. You could put him in at center if you wanted to. And he'd probably do just fine, especially in that particular forum where Team USA was so much better than everybody else. Anyway, how many 5-person lineups, 5-man lineups are possible? You have 12 players here on this team. And we're trying to choose 5 players. And the thing is, we're going to say position matters first. So not that the players assigned position matters in terms of what they normally play, but we're assigning the players to actual positions on the floor for the game. So you got the point guard position, the shooting guard, the small forward, the power forward, and the center. And again, you can put any player at any position. How many are possible? So the simplest way to think about this is, how many choices do you have for the first position, the 1 spot? And since you have 12 players, you have 12 choices, right? You could put any player in at point guard. Once you pick your point guard, this is conditional probability, right? We're not doing probability, but it's basically the idea is we've already picked one for that first spot. So now there are 11 left to choose from, right? So let's say that our first spot was Magic Johnson, which maybe makes the most sense. Magic. Then how many choices do we have left for the 2 spot? Well, there's 11 left, right? 11 choices left there. I'm going to go ahead and actually I'm going to write my 1 example lineup over here instead of right above it. I don't want to confuse the issue here. And I'll erase Magic up here. Because again, we're representing all of the possible lineups up here. 12 choices for the first spot, 11 for the second. And you probably got this figured out. If you didn't at the beginning, you have 10 choices left for the 3 spot. Once you've placed those 3 players, there's 9 left to choose from for the 4 spot. And then finally 8 left for the 5 spot. So the answer to that question, how many 5-person lineups are possible out of these 12 players if position matters, if putting them in different positions makes a difference, is 12 times 11 times 10 times 9 times 8. I want to talk about that a little bit more, though. But let's put a sample lineup up there. So one very common lineup to do would be Magic at the 1 spot, Jordan at the 2 spot, maybe Larry Bird at the 3 spot, perhaps Karl Malone at the 4 spot. And then, I don't know, did Barkley? Oh, Barkley was the 4. Ewing probably started, but Robinson's the man. I'm going to throw him in there. So many good players to choose from. And so there you have it. There's one of the lineups. How many are there? Well, there's 12 times 11 times 10 times 9 times 8, which is a little less, I think, than 100,000, but in that neighborhood. So what do we do with that? Well, first of all, I just want to point out what we just counted. We counted again how many different lineups are possible, where the position matters. So this lineup here is different than if I switched, let's say, just Magic and Jordan and kept everything else the same. So let me take this and duplicate this here. And let's just switch Magic and Jordan. And my point is, that is a different lineup. Maybe Jordan one day at the beginning of the game says, you know what? I want to bring the ball up today. Let me play the 1, right? Well, that's a different lineup according to this count, right? Because there we would have picked Jordan first, and then Magic would have been one of the 11 choices to put there. Okay, so as long as we understand that. What we're talking about here is permutations. This is permutations. This is 12p5, the number of ways that you can pick 5 elements, in other words, in this case, 5 players, out of a group of 12 players in an order, right? So notice we picked the same 5 players twice here, but they counted 2 different times because they're in different orders. So the order matters with permutations. Permutations, order matters. Okay, and so our permutations formula here, we had 12p5. It came out to 12 times 11 times 10 times 9 times 8. But there's a way to write this that's a little more formulaic. We can kind of generalize it more. Anytime that you find yourself multiplying by consecutive integers like this, descending toward 1, you can use the factorial. So just to give a for instance, if you don't know what it is, 5 factorial would be 5 times 4 times 3 times 2 times 1. You keep multiplying by consecutive integers in descending order until you get to 1. So we can do that here. We can say, well, this is 12 factorial, except you might be thinking, well, what about 7 through 1? We don't have those. So, okay, that's all right. We'll just put a 7 factorial on the bottom because if you think about it, that 12 factorial could be written as 12 times 11 times 10 times 9 times 8, and then times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Well, that's 7 all the way down to 1. That's 7 factorial. So that's another way to write 12 factorial. And on the bottom, we have 7 factorial. And we can actually reduce out, kind of cancel out those 7 factorials, which leaves us with what we wanted, right? Why write it this way? Well, it's simpler. It's less to write. And it's also more formulaic because now what we can say is permutations NPR, the number of ways that you can permute R elements out of N elements, the number of ways you can place R things in order out of N things is N factorial, that's the 12 factorial on top, divided by N minus R factorial. What that does by taking N minus R is after you do R items, right? 1, 2, 3, 4, 5 in this case, right? We've placed our 5 players. Everything else will get canceled out by that N minus R factorial factor. Okay, so this is the formula for permutations, the number of ways that you can place R things in order out of N things. Okay, now suppose you're Chuck Daly, the coach of the dream team. You got this team and, you're messing with different lineups and you got this lineup and you've done it a few different ways. And, because Jordan wants to play the point one day and I don't know, whatever. You're just mixing things up. And eventually you're just like, does it really matter? We just beat Angola by 45 points. Who cares? Actually, I think it was more than that. Who cares what position we play? So let's just say you 5 get out there and play, right? So now we're talking more combinations. And I feel like basketball has gotten more like this over the years. The positions have kind of morphed and they're a little more ambiguous and, players play more fluidly. You can have a lineup with 3 shorter players or 5 shorter players all shooting 3-pointers. I don't know. So anyway, you got 12 players. And let's just kind of put them all in the same category. It doesn't really matter where they play. The question now is how many groupings of 5 players are possible, right? Ignore the positions, just how many groups of 5 are possible. So the difference now is that these 2 permutations are going to count as just one combination. I don't want to count that twice. So the easiest way to think about this is to say, well, for each lineup that we made here, right? For each lineup, for each group of 5 players, how many times did we count it, right? Like these are 2 right here. These are 2 different permutation lineups, but they're the same 5 players. They're the same combination. how many different permutations can I have with the same 5 players? So let's just focus on those 5 and let's answer that question. How many permutations were counted for this combination or for any combination? Combination. So again, these are 2 permutations of one combination, but there are many more, right? So assume we have this lineup of these 5 guys, Jordan, Magic, Bird, Malone, and Robinson. My question is, how many times did we count it? Well, we had 5 positions, and every ordering of those 5 players is the same combination. How many choices did we have for the first player with those 5? Well, 5, right? And then once we pick, say, Jordan to play the 1, now you have 4 choices left for the 2 spot, 3 for the 3 spot, 2 and 1. And so that's a 5 factorial, or 120 different permutations for each combination. That was 120 for this combination. That's going to be true for any 5 players you choose, though. There are 120 different orders that we counted up here. And the thing is, we don't want to count all those different ones separately down here, because down here we're talking about combinations. So what we're going to do is we're going to take the number of permutations divided by the number of permutations for each group. The number of permutations for each group. You get the idea. The number of permutations for each combination. So what we're going to do is we're going to take that 12 factorial divided by 12 minus 5 factorial, right? That's 7 factorial. And we're going to divide it by this 5 factorial. That gives us the number of combinations. And so in this case, it'll be 12 factorial over 7 factorial times 5 factorial. Notice that these 2 numbers add up to 12. That's how that works in the combinations formula. More generally, the combinations formula looks like this. NCR, which can also be written in this notation. And you can say N choose R. You have N elements. How many ways can you choose R of them, right? Again, order does not matter here. Is equal to N factorial over N minus R factorial times R factorial. So that's the formula. Hopefully the formulas make sense now. You can look up those formulas anywhere. They're pretty well known and widely used, but they're not magic. They do make sense. Magic Johnson is magic. These formulas are not. So I hope that helped. Thank you.